Yes, grade 12s, how are you? I hope you are doing well. This is Kamala, tutor and educator for mathematics and physical sciences, grades 10 to 12. Now, today I want us to do our physics for grade 12, and we're starting from the first topic, which is momentum and impulse. Yes, momentum and impulse. This is video 1, and this is the year 2025. We are starting it this very first of January 2025. Yes, this is Kamala, tutor educator. If you want to know more about our extra classes, you reach us on 0785 222 041. Yeah, we are starting now this video 1. Now this momentum. What's momentum? Now momentum is the product of mass of an object and its velocity. Momentum is what? Momentum is defined as the mass, the product of the mass of an object and its velocity. Let me get a red color here. Momentum is the product of mass of an object and its velocity. So when you multiply, when you multiply the mass times velocity, what you get is called the momentum. So in other words, momentum can be thought of as quantifying the motion of an object. Let me explain something here. You know what, guys? If we have a big bus, maybe carrying 52 people, and then a quantum, maybe carrying 20 people or 27 people. Now, the bus carrying 52 people is not easy to turn. Okay, when you're turning a corner, when you're in a corner, it's not easy to turn because it is if they have the same speed. I repeat, I'm saying that momentum, we can use it when we are quantifying the motion, okay? When we are quantifying the motion of an object. So to quantify the motion of an object is what we mean that if you consider a big bus and a small car, you can easily turn when you're driving a small car because the smaller car has got smaller momentum, even though they all have the same speed. But because the masses are different, so the bus is going to have a bigger momentum. So in other words, the bigger the mass, the bigger the momentum if the velocity is constant. Okay, let us proceed here. Now to get momentum, the formula says that momentum equals to mass times velocity, where P is momentum must be in kilogram meters per second. Then the mass must be in kilograms, and then the velocity must be in meters per second. Otherwise, you must change it. If they give it in grams, it must be in kilograms. Then you can get your momentum, that is P equals to mass times velocity. Hope we are still together. Then now the vector nature of momentum. So momentum is a vector quantity and it has both magnitude and direction. I repeat, momentum is a vector quantity, so it has both magnitude and direction. So in this particular case, it is therefore important to always include direction in all momentum calculations. Let's have an example here. For example, they say here a golf ball of mass 0.05 kg. Okay, so you see we have the mass. They're saying the mass is what? 0.05 kg. That's our mass. Okay, then they say leaves a golf club at a velocity of 90 meters per second. This is our velocity here, 90 meters per second in an easterly direction. Then they say calculate the momentum of the golf ball. So looking for the momentum, that's P. Okay, so we have the mass in kilograms and we have the velocity in meters per second. So we just say momentum equals to mass times velocity, and then we substitute. The mass is what? 0.05. What about the velocity? It is 90 meters per second, where in the easterly direction, so we can choose east as positive. So if you choose east as positive, then you're going to get 4.5 kilogram meters per second east. Okay, that's how you get our momentum. So if the question says calculate momentum, you say momentum P equals to mass times velocity, and then you do what? Then you substitute for the mass and the velocity. Don't forget, the mass must be in kilograms. What about velocity? Meters per second. I hope we are still together. This topic is so interesting, though sometimes challenging. Now we talk to call about change in momentum, the change in momentum, the change in momentum. Okay. Now change in momentum, when a net force acts on an object, it results in a change in the velocity for the object and therefore a change in the momentum of the object. I repeat. We're saying that when, okay, we're saying that when the net force, okay, when the net force acts on an object, okay, what happens? It results in what? In a change in the velocity of the object and therefore what? A change in momentum of the object. Okay. So momentum is going to change because we have got a change in the velocity. Okay. Because we have what? A change in the velocity. Now to get our change in momentum, this is the formula here. It says that change in momentum equals to final momentum minus initial momentum. I repeat here, if they say calculate the change in momentum, what do? You first get your final momentum, that is P final, okay, P final. Then you also get your initial momentum, and then later you subtract the two, okay. When you subtract it, you get change in momentum. You're going to say change in momentum equals to what? Final momentum minus initial momentum. Okay, all right. Let us proceed. Hope we are still together. Let's continue here. Now, so because of the vector nature of momentum, it is very important to choose positive direction, okay? Because you're going to define your answer, whether it is to the east or to the lefty, right, anywhere, depending on your choice, okay? Let us look at this example here. It says that it says that 1,000-kilogram car initially moving at a constant velocity of 16 meters per second in an easterly direction approaches a stop street, starts braking, and comes to a complete standstill. Calculate the change in the car's momentum. I repeat, a car of this mass, this is the mass here, which is 1,000 kilograms altogether, initially moving at a constant velocity. So this is the V initial. The V initial is what? Is 16 meters per second, okay, in an easterly direction. So if we take east positive, it's going to be positive 16, okay. Then approaches a stop street, starts braking, and comes to a complete standstill, meaning our V final here. If they say complete standstill, it means what? That the V final is 0, okay. It means V final is what? V final is 0. Okay, then they say calculate the change in the car's momentum. Now to get our change in momentum, like I said in our formula, change in momentum, okay, equals to what? Equals to final momentum, okay, minus what? Minus initial momentum, okay. So because east is our first direction here, we can choose it to be positive. So we say choosing east as positive, then we can now how do we find final momentum? We're going to use mass, okay, times final velocity minus mass times initial velocity. Then we can substitute and then get our answer like this. Okay, so the mass is 1,000, then final velocity was 0. What about initial velocity? It is 16. Because we choose east as positive, that's why, guys, we are putting positive 16 here. This is positive 16 here, okay. So with our calculator, it's going to give us negative what? Negative 16,000, okay. But because momentum is a vector, this negative must be explained. That's why in our answer, we should say that the change in momentum is going to be what? 16,000 kilogram meters per second west. Why do we say west? Because we chose east as positive. I hope we are together. Now, our other example here, the other example says here that a cricket ball with a mass of 0.2 kilograms, this is our mass here, mass of 0.2 kilograms, this is the mass here, okay. They say approaches a cricket bat at a velocity of 40 meters per second, okay. So this is our V initial and is east. Are we together? and it leaves the cricket bed at a velocity of 50 meters per second. So now this is our V final. Okay, this was V initial. Now this is V final, 50 meters per second west. Okay, it is going to west. The first one is going to east. Okay, let's calculate the change in the ball's momentum. Okay, during its contact with the cricket bat. Okay, so we need change in the momentum again. We need the what? Change in the momentum. But don't forget that we must choose direction. Again, if we choose east as positive, how do you find change in momentum? Z change in momentum equals to final momentum minus initial momentum. Okay, final minus what? Initial momentum. And how do you find the final momentum? Mass times final velocity. What about initial momentum? Mass times v initial velocity here. Now, if we do substitute our mass here, it was 0.2 kilograms, which I think you guys can see here. And then I will choose east positive. It's going to be positive 40 for the v initial. Now, because it leaves 50 meters to the west, it's going to be made negative on the 50, because if east is positive, then west must be negative. Hope we are together. That's why in here we are saying MV final, but final is negative 15. Eh? What about the initial is positive 40? Hope you can see that here it's positive 40. This is negative 50. So with our calculations here, what's our change in momentum? Is negative 18 after our calculators here. But if you multiply here 0.2 times negative 50, what do you get, guys, here? What do you get, guys, here? We get negative 10, right? Negative 10 here. Okay. What about here? 0.2 times 40, we get it is 8. So this is 8. So minus 10 minus 8 gives us minus 18 here. So our change in momentum is what? It is 18 kilograms per second west. Why do we say west? Because we chose east as positive. So, and we are getting a negative answer here. So we should conclude and say that it's going to be 18 kilograms per second west. Okay, now before I continue, now this change in momentum, sometimes they can ask you to draw a graph to indicate the change in momentum and the final and the initial momentum. Okay, let's take one as an example here. Now in this case, as you can see here, if we have it like this, okay, remember we chose east as positive, né? And our initial was what? Our initial momentum. So here it's like this. It is 8, né? I want us to do something here. Our initial momentum is 8. Okay, this is our P initial. It is 80 kilograms per second east. Ne? Are we together? It is 80 kilograms per second east. Are we together? And then our P final or final momentum, okay, is given by, we saw it is negative what here? Hope it was negative 10. Hope you remember this. It's negative 10 here, right? So I'm going to put here negative 10 kilogram meters per second, kilogram meters per second. Okay, so because of the negative, I don't put the west, but it means it's going to the west. Now, what about our change in momentum? Now, our change in momentum, we can get by our graph as well, but just put it here. We got as negative what? Negative 18. Okay. All right. Now, I want to show you how we can do this on the graphs here. Now, we are choosing east as what? East as positive, ne? So watch this, guys. If I come here and I draw my first P initial, okay. Now I'm choosing. You see, this east is it is 8. Okay, so 8 must be shorter than the 10. Okay, so if I draw it from here, for example, going like this, okay, that's the east, and that's our V initial, our P initial, which we are calling the 8. Okay, that's our 8 there. That's our 8 there. So this is our P initial here. P initial, which is 8. Okay. Now here we have got two alternatives. I can start from the head of the first vector here, which is the p initial. Then I draw the other vector now. Now the other vector which I have here is what? It is p final, which is negative 10. Now being negative, it must be facing to the westness. So I draw it like this, okay? Let's draw it like this now. Remember that this one must be longer than what? Than this other one, because this one is now 10. So being a negative, it is facing to the west. What about positive, facing to the eastness? So in this particular case, let me just put it in a different color. Let me choose green here. Okay, so now here, if I want to get my change in momentum, okay, what I'm going to do, I have the tail here for the first vector, like this. Then from this point here also, okay. Now I'm gonna draw now my change in momentum here. Now I can draw it like this. Watch this now. I'm gonna start from here. And then draw all the way until I finish the first vector, which was the p initial up to here. You see that, guys? Ne? Let me put in a different color now. So let me give it a pink color. Okay. So what you see here, guys, this one is my p initial. Okay. This is my p final. Are we together? And this is my change in momentum. Now, what is most important here for you to notice that the arrows must be pointing the right directions, and the magnitude must be the same in here. You don't have, because it can be changed. Now you can find out that someone else can draw it like this. Let me show you how as well here. Someone can also draw it like this. They can come here. Let me see, like this one here. Just get a copy. Okay. Now this one, which was p initial, they can draw it like this. Okay. And then the p final, get a copy as well here. And then they draw it like this. Okay. This was the p initial. Then when they put their p final like this. Okay, from this point here. Are we together? And then this particular case now, now they can draw their change in momentum like this. Okay. They can draw it like this. Now I want you to note something that this change in momentum is still the same magnitude and facing the same direction. Even this initial momentum, this final momentum is still the same magnitude, also facing what? West. The P initial, same what? Same size, also facing east. So these two answers, they are all correct and they are all the same. Okay. Alright, let's continue here to another example. Another example here. Now this question came last year, 2024, in May, June. Okay, so if you're writing May, June, pay attention. Now the question says that this is 2024 May, June. You can see it here. They said here that the vector diagram below shows the initial momentum P1, the final momentum P2, and the change in the momentum, that's delta P, for a car that moved on a straight horizontal road. I repeat, the vector diagram below, this one here, it shows the initial momentum P1, the final momentum P2, and the change in momentum for a car that moved on a straight horizontal road. Okay, so this is P initial, P final, change in momentum. Now the question says here that which one of the following sketch graphs correctly shows the momentum of the car for the time the car moved on the road? So we have to choose from these four here. Which one is correct? Is it A, B, C, or D? Okay, let us explain again. Now I repeat, the question says like this. It says that the vector diagram below, this one here, It shows the initial momentum P1, the final momentum P2, and the change in the momentum delta P for a car that moved on a straight horizontal road. Now I will ask you guys, if you look at P1 and P2, you see they're all pointing to the east. Are we together in the same direction? But which of the two is bigger? Is it P1 or P2 in magnitude? You guys can see that this P1 is longer than P2. In other words, the P1 is bigger in magnitude than P2. So in physics, if the arrow is longer than the other one, it means it's of a bigger magnitude than the shorter arrow. So because the two arrows are facing the same direction, it means that it means that we are not we are not we are it means that the car is moving in the same direction. I repeat, because the two arrows, the initial momentum and the final momentum, they are facing the same direction. It means that this car is going the same direction. Why? Because we saw in this explanation here that this one was going to the east, this one was going to the west. You see, the air directions are different now, okay? Because they're facing opposite direction. But in here now, because they're facing the same direction, it means even the cars going the same direction. Now, when it comes to our graphs here, whenever we are moving the same direction, then we should be on one side of the y-axis. I repeat, whenever the object is moving in the same direction, then the graph must be on the same side of the y-axis, which means that in this particular case, graph C and graph D, they are not correct because they show this direction and this one here. Actually, here we are reversing in direction, so this is not correct because our arrows are both pointing in the same direction. So now we're going to choose from A and B. Now, our answer is either A or B. But how do we know the right answer now? You look at our thing again here. If you look at P initial and the P final, which one is bigger? P initial. So we're going to compare A and B. Which one has got a bigger P initial and a smaller P final? Now, from 0, okay, like this. Yeah, I think to make it more. Now, you see, if this is 0 here, this is momentum, ne? So if you check here, this is P1, this is P2. What are the values here? You can put a bit of value. You can say if this is let me say if this is 20, this can be 16 or 14. Are we together? Now check here, guys. This is P1, this is P2. Okay. This one can be now the 14. What about here? This can be now the 20 or 25. So if you look at our two graphs A and B, which of the two has got a higher P1? Is it graph B or graph A? We can see it is graph A because with graph A, the P initial is higher than the P final. As we see from here, the size or the magnitude for P1 is bigger than for P2. So the answer is going to be A. That's why in this particular case, our answer is A, and the both graphs must be on the same side of the graph because the arrows are facing the same direction. I hope you guys were together. Let us continue here. Let's talk about Newton's second law of motion. How do we state it? Now, Newton's second law in terms of momentum, we stated that the resultant or the net force acting on an object is equal to the rate of change of momentum of the object in the direction of the resultant or net force. I repeat, they can say state Newton's second law of motion in Newton's second law in terms of momentum. Okay. So if they say state Newton's second law of motion in terms of momentum, this is what you say. What do you say? You say that the resultant, okay, or the net force acting on the object is equal to the rate of change of momentum of the object in the direction of the resultant or net force. Okay, now how does it come about? I will show you just now. Just look here, watch this. We know from the grade 11 that Newton's second law has got an equation, that is to say, we know that our F net, okay, we know F net equals to what? If you remember this, guys, F net equals to mass times acceleration. Are we together? But what do we know about acceleration? The same as saying change in velocity, okay, over change in time. That's acceleration. Hope we are together. And I've talked about change in velocity. What does it mean to us? It means you're going to have what? You're going to have the final velocity, okay, minus what? Minus initial velocity, are together, divided by change in time. Divided by what? By change in time. Okay, divided by change in time. Now, if I open brackets here, I'm going to get F net, okay, F net equals to the mass times V final, that's M, V final minus mass times V initial, that's M V initial here, divided by what? By change in time. Okay, but we have just discussed that what is mass times velocity? It is momentum. What about mass times final velocity? It is final momentum. It's going to be now? It's going to be P final, okay, minus what, guys? Minus P initial, okay. But what does it mean to us? If we say P final minus P initial, we say the same as what? Change in momentum. Change in momentum divided by what? By change in time. So you can see that now our F net or our net force, okay, our net force, which is F net here, our F net is equal to change in momentum, okay, divided by change in time. And we also saw that also our F net, okay, our F net, we have just seen this, our F net equals to mass times acceleration. Now, so from this, because it's the same F net, that's why we say that the net force acting on the object is proportional, is equal to the what? To the rate of change in momentum of the object. I repeat now. So that's how we have this formula here. That's how we get it. I repeat the statement here. We are saying here that again that if they say state Newton's second law of motion in terms of momentum, is what? We say that the net force acting on an object is equal to the rate of change of momentum. That's what dividing by change in time of the what? Of the object, the direction of the net force. Hope we are together. Don't forget that in this case our F net is resultant force and delta P is change in momentum. What about delta T? Time in seconds. Okay. Hope we are still together, guys. That brings us to impulse. That brings us to impulse now. So what is impulse? What is impulse? What is impulse? Now, impulse is the product of the net force acting on an object and the time for which the net force acts on the object. I repeat, if they say define impulse, so that impulse is the product of the net force acting on the object and the time for which the net force acts on the object. I repeat with an explanation again. So our impulse, okay, pardon, our impulse, okay, impulse is the product, meaning multiplication, all together, of the net force, all together, and the change in time for which the net force acts on the object, or the force acts on the object. If they say define impulse, you say impulse is the product of the net force and the change in time for which the net force acts on the body. So by rearranging Newton's second law in terms of momentum, yeah, we saw that our F net, remember me, we said our F net, okay, F net equals to change in momentum, okay, divided by change in time, right? Which means if we cross multiply, we're going to get what? We're going to get F net, okay? We're going to get F net times change in momentum. Change in time equals change in momentum. So in this particular case, if we rearrange the equation, that is what we get here. So from here, what we observe, guys, is that our impulse equals to the net force times change in time, right, together. But also we see that it is also equal to change in momentum. So in other words, also impulse equals to what? Equals to change in momentum. Okay, so mean that, but what's our change in momentum? It's mass times change in velocity. No? So mean that our change in momentum equals to what? To mass times change in velocity. No? Now this one brings us to what we call as the impulse momentum theorem. I repeat, it brings us to what? To the impulse momentum theorem. And how do we state it? That impulse is equal to the change in momentum of an object. Okay, that's what I mean by the impulse momentum theorem. We say that the impulse is equal to the change in momentum of an object. Don't forget, impulse can be measured in Newton seconds. Why? Because force is newtons. What about change in time? In seconds. And then what about change in momentum? Measured in what? Kilogram meters per second. Okay. Now the change in momentum is directly dependent on the magnitude of the resultant force and the duration for which the force is applied. Impulse is a vector quantity. That's to say, it's what? It must be directionally specific. Let's look at examples here before we stop there. I have an example here. We say that a golf ball with a mass of 0.1 kg is driven from the tee. The golf ball experiences a force of 1,000 newtons while in contact with the golf club and moves away from the golf club at 30 meters per second. For how long was the golf club in contact with the ball? I repeat, they say that a golf ball of this mass, this is the mass of the golf ball, is driven from the tee. The golf ball experiences a force, this is a force here, of 1,000 newtons while in contact with the golf club and moves away, okay, moves away, okay, from the golf club at what? At 30 meters per second. Then they say, for how long was the golf club in contact with the ball? Now, if they say for how long, we're looking for the change in time. Ne? So we know the force, we know the mass, we know the velocity here. It is moving away altogether, and then we know the v initial was 0. Okay, so here you're gonna use f net times change in time equals to mass times change in velocity. So because we know the force as 1,000, we just substitute it here and look for this t here. The mass is 0.1 kg. What about final velocity? It is 30, then minus 0 altogether, and then it gives us t as what? As 3 times 10 to the power negative 3 seconds. Okay, hope we are together. Now, another example here, it says that why can airbags be useful during a collision? State your answer by using the relevant scientific principle. Why are airbags useful during a collision? Otherwise, why do we need airbags? Now, this reason here, it's because the change in the momentum remains constant. Okay, I repeat, the change in what? Momentum remains constant, but the use of the airbags prolongs. So the airbag does what? It prolongs the time t of impact during the accident, okay, or during the collision altogether. So the resultant force experienced is inversely proportional to the contact time, and therefore resulting in a smaller resultant force. That's why they are helpful. I repeat. Now we said that in our explanation that our change in momentum, remember, our force, okay, the force equals to change in momentum divided by change in time altogether. So this force here, because of the accident, is going to be smaller. Why? Because of the increase because of the increase in what? In change in time, which is caused by the airbag. So the airbag is we're gonna have a bigger change in time, and therefore we're gonna have a smaller what? A smaller force, because change in momentum is constant. That's why the airbags are important. From here you can see that our force due to the collision is proportional to what? To 1 over change in time, because change in momentum is a constant. Okay, let us proceed here. Our other example here, what does it say? They say that the following graph shows the force exerted on a hockey ball over time. The hockey ball is initially stationary and has a mass of 150 grams. Okay, and then they said that this is the graph here. What do you have on the y-axis of what force newtons? In this time in seconds here. Calculate the magnitude of the impulse, that's the momentum of the hockey ball. I repeat. The question says that the following graph shows the force exerted on a hockey ball over time. Okay, the hockey ball is initially stationary and has a mass of what? Of 150 grams. Okay, then they say here that what do you have on the y-axis? This is force in newtons. What about here? What do we have? Time in seconds. They say calculate what? The magnitude of the impulse. That's the momentum of the hockey ball. Now, what do you know about impulse? Do you remember, guys? So that okay, impulse equals to the force times what? Times change in time. Now, here we have the force on the y-axis. What about change in time on the x-axis? So, whenever we have the length this where you have got the what we have the force on the y-axis. What about here? Time on x-axis. So this must give us a clue that we should find the area under this graph. It must give us the impulse. Now this one being a triangle, how do you find the area? We say it's a half, okay, times base times height. So in this case, what is our base? From 0 to 0, 0.5 is going to be 0.5 here, okay. What about our height? It is 150 newtons. So here we should get our answer now. So we're gonna say a half, okay. That is 0.5, okay, times another 0.5, okay, and then times what? Times 150. So it gives us what? It gives us 37.5. 37.5. So here we have 37.5. We have 30 what? 37.5 Newton seconds. That's our impulse. Okay. So that's what we do here. I hope we are together, guys. Now our last example for this lesson, it goes like this. So we have this question here. What does it say? It says that let's check it from the start here. Hope you guys can see this. The graph below shows how the momentum of car A changes with the time just before and just after head-on collision with the car B. Car A has a mass of 1500 kilograms, while the mass of car B is 900 kilograms. Car B was traveling at a constant velocity of 50 meters per second west before the collision. Take it as positive and consider the system as isolated. I repeat, the graph below shows how the momentum of car A changes with time. So this graph is for only car A. There's no car B here. This is for car A. This is for car A, okay? And this is momentum on the y-axis, and this is change in time in seconds, okay, for car A. So they said that car A has a mass of what? 1,500 kilograms. That's the mass of car A. While the mass of car B is what? 900 kilograms. They say car B was traveling, okay? Car B was traveling at a constant velocity of 15 meters per second west before the collision. Take east as positive and consider the system as isolated. Okay, what must we do then? They say, what do you understand by the term isolated system as used in physics? So now a system is said to be isolated if the net external forces acting on the system is zero. I repeat, so that a system is said to be isolated if the net or resultant external forces acting on it is zero. Okay, next question here. They say use the information in the graph to answer the following questions. Calculate the magnitude of the velocity of car A just before the collision. Just before the collision. Look at our graph again, people. One more time. This is a graph for car A, right? So because it's for car A, we can see from this point to this point, if I come up here, this must be this is momentum. This must be my initial momentum. This must be my initial momentum. And it is for what? It is for car A, which is 30,000. Okay. What about here? This is where we have the change in momentum. Okay. What about here? This is my final momentum. For what? For car A, not for car B. Okay. Now they gave us mass of car A. How much they say it is what? It is 1500. I think you see it here. Now they want the velocity of car A just before the collision. So because we have the initial momentum, okay, then why not? We said from the start that momentum, okay, equals to mass times velocity. So if we have the initial momentum, then we can be able to do what? To say mass times what? Times v initial. So initial momentum we see it is 30,000. So this is 30,000 here. Okay. What about the mass? We said 1500, 1500 times v initial. So our v initial equals to 30,000. Okay. 30 from here, 30,000. Okay. Divided by the mass of the car, which is 1,500. Let's confirm here the mass. Yeah, that's correct. So now to get our answer here for the v initial, we're going to get what? If we divide here, if we divide the 30,000, okay, 1, 2, 3, 4, divided by what? By 1500. It gives us here 200, so it is 200 meters per second. Now do they want magnitude or they want velocity? Let's check it here. They want magnitude, so they don't need direction, but we know it is east because they said here car A is moving east, right? East, because they said the car B is traveling west, then the car A is moving east. Okay. So what else do we need? Calculate the velocity of car B just after the collision. Now car B after collision, I must use conservation of linear momentum, which is in the video 2. So I'm skipping this one for now. But now if you subscribe, you can subscribe and watch our video 2, which is coming just soon. Then they say here, calculate what? Magnitude of the net average force acting on car A during the collision. Okay. Now this is car A, and I want average net force acting on car A during collision. So from here, from 20.1 to 20.2, that's when this car A undergoes collision. Okay. So my F net, what do I know? Our F net, okay, equals to change in momentum, okay, divided by what? By change in time. So looking for the net force. What's my change in momentum? So it is final momentum, okay, final momentum minus what? Minus initial momentum divided by change in time, okay. So in this particular case, what's our final momentum, guys? We see it is 14,000 here. This one here is our final momentum here, which comes here. What about initial? It is 30,000, okay. So I'm going to say this is 14,000 minus 30,000 minus what? Minus 30,000, okay, divided by change in time. That means from 20,1, 20,2, I'm going to say 20,2 minus 20,1. So it gives us what here? Let's check it out, guys. Now, if we check it here, what do we have? So we have 14,000, okay, minus 30,000, okay, divided by 20, comma 2 minus 20, comma 1. So it gives us negative 160,000. Negative 160,000. Now that is a net force, ne? Must be newtons. Do they want magnitude or they want force? Let's check it out. They say magnitude. So in that in this case, we just forget about the negative. So therefore, it's gonna be 160,000. Alright, guys. Thank you so much for watching our video one. Please try this exercise, and if you have no extra classes, you can connect with us tonight. Then we do the solutions together. However, if you're not in our extra classes, you can join us on 0785 222041. So try these questions out and we'll mark them together. Thank you so much for watching. Bye bye.